Problem 1. A parallel plate air-filled capacitor has plate area of 10 power minus 4 meter square and plate separation of 10 power minus 3 meter. It is connected to a 0.5 volt 3.6 gigahertz source. The magnitude of displacement current is given epsilon is equals to 1 by 36 pi into 10 power minus 9 farad per meter. Now the solution to the given problem. What is the given problem? Just you observe the description that a parallel plate capacitor was given to us with plate area S is equals to 10 power minus 4 meter square and the distance is given to us between the plates, that is 10 power minus 3 meter. The potential which is applied is 0.5 volts and frequency of operation of the source is 3.6 gigahertz and epsilon is given to us, which is nothing but the epsilon naught 8.854 into 10 power minus 12 farad per meter. What we have to calculate is the displacement current density or the displacement current we require. So for the obtaining displacement current, what are the parameters we are supposed to observe? So the displacement current is not at all defined till now. So what I do is just I will give you the solution for the current. So how the current can be obtained? The current can be obtained with the simple equation, that is dq by dt. That is the rate of change of charge is equals to current, right? Here instead of taking the differential quantities, directly we will consider the charge per given time. The charge per given time is nothing but the current. So this can be once again rewritten like this. 1 by time is the frequency, so frequency into charge. So the current can be calculated using the frequency and charge, but just to observe the data, there is no charge is given to us. Instead of charge, the potential is given to us and distance between the plates and plate area is given to us. So quickly recollect the equations what we have which can relate the charge with all these parameters. So here clearly what we have is C is equals to Q by V, that the charge can be calculated using capacitance as well as the potential. From this one, Q is equals to just CV. So if you know the capacitance and multiply that one with the potential, then we will get charge. So initially what we have to do is we have to obtain this capacitance. So capacitance for a parallel plate capacitor is epsilon S by D. So that epsilon is nothing but the epsilon naught what is given to us, that what I write here 8.854 into 10 power minus 12 into what is S here 10 power minus 4 divided by D, distance between plates is 10 power minus 3. So after simplification, simply what we get is 8.854 into 10 power minus 13 farads. Simply this is the value of our capacitance. Now what we have to do is you have to multiply this capacitance with the potential what is given to us. Therefore clearly Q can be obtained as Q is equals to 8.854 into 10 power minus 13 multiplied with the potential. Potential is 0.5, that is 1 by 2. So which is equals to, simply it is 4.427 into 10 power minus 13 coulombs. Since we are calculating the charge, it is coulomb. So we obtained the Q and we have already frequency. So F into Q will give us the current, that is the total current what we can observe is equals to Q. What is Q? Approximately 4.4 into 10 power minus 13 multiplied with our F is 3.6 giga, that is 3.6 into 10 power 9. So the approximated answer, so maybe this is 16 into 10 power minus 4, which is equals to approximately 1.6 milliamperes. This is our answer. So here just what we have to do is, if you have calculator, go for the exact one, and if you have no calculator, take the approximated multiplication of these two, that 1.6 milliamps. So simply once again just observe what we want is the current. Current can be written as Q by time, which is nothing but frequency into charge. Since the frequency is given to us, we are doing in that particular fashion. So this is the solution for this particular problem. Problem 2. The electric field on the surface of a perfect conductor is 2 volt per meter. The conductor is immersed in water with epsilon is equals to 80 epsilon naught. Then the surface charge density on the conductor is given epsilon is equals to 1 by 36 pi into 10 power minus 9 farad per meter. Now the solution to this problem. Just observe what is the given data. The electric field intensity is given as 2 volt per meter for a conductor, and epsilon is equals to 80 epsilon naught, and we require the surface charge density when that particular material was immersed in water, right? So whenever it is immersed in water, what we require is the surface charge density, how much charge will be appeared on the surface. If we calculate the total flux leaving through the water, just what I assume is that particular water what we have is the Gaussian surface. So what I do is I will calculate the total flux leaving through that Gaussian surface, then the total charge enclosed within that one is nothing but the total surface charge what we require. So here what I am doing is I am once again bringing that Gauss law here, and I will try to solve this problem. So clearly the total flux leaving is equals to the charge enclosed. This charge can be calculated using its surface charge density. That is what is to be calculated, and the total flux leaving can be calculated using its flux density. So just you observe here, this is integral d ds. The total flux density is d, and the total flux is integral d ds. This is a surface integral, which is equals to the total charge can be calculated using its charge density, that is surface integral of rho s ds. So a very simple relation. So if you compare them, this is rho s dot ds. If you compare them, clearly we can say that d is equals to rho s. That is the surface charge density is equals to the electric flux density. So if you calculate this electric flux density, obviously the answer is the surface charge density. How the electric flux density can be calculated? Using our epsilon naught E. Since directly it is not epsilon naught E, so directly what I do is I will write this one as epsilon E. Since it is a material that what I am considering, it is epsilon E is equals to rho s. Therefore, so rho s is equals to, what is epsilon here? 80 into epsilon naught. That 80 into epsilon naught can be written as 8.854 into 10 power minus 12. That is equivalent of this one I am writing here. 80 epsilon naught into what is electric field intensity? Simply it is 2. So approximately we can write answer so like this: 144 into 10 power minus 11. So rho s is equals to 144 into 10 power minus 11. If you rearrange this one, 1.44 nano, that's into 10 power minus 9, 1.44 nano coulomb per meter square. This is our answer. It's nothing complex in this particular problem. Just what we are supposed to do is we are supposed to observe what are the given parameters to us. Here the electric field intensity is given to us, epsilon is given to us, and we are supposed to calculate this rho s. Just using our Gauss's law, we can derive this simple relation that d is equals to rho s, and after that one we can calculate that one is approximately 1.44 nano coulomb per meter square. This is the answer. Problem 3. The space between plates of a parallel plate capacitor of capacitance C is filled with 3 dielectric slabs of identical size as shown in figure. If relative dielectric constants are epsilon R1, epsilon R2 and epsilon R3, the new capacitance is. Now observe the solution for this particular figure what is given to us. Here 2 parallel plates were considered, 2 parallel plates were taken. This is one parallel plate and this is another parallel plate. Between these 2 parallel plates, 3 dielectric slabs of same size were placed. So without these dielectric slabs, the capacitance is C. So whenever we are inserting these dielectric slabs, how the capacitance will be modified? That's what we require. For that, we need to observe this particular arrangement. Here, what is the arrangement we are considering? For this plate, the potential is applied. For this plate, the potential is applied. And if you take them as 3 different capacitors, so these 3 are 3 different capacitors, that what we can observe. Up to this part, this is one capacitor, and up to this part, this is one capacitor, and the third one is third capacitor. So here 3 capacitors were given, and for these 3 capacitors the potential is same. Just imagine what is that particular arrangement. If the potential is same for all the capacitors, then they are connected in parallel. So the equivalent of this one can be drawn as a 3 capacitors which are connected in parallel. That the arrangement is like this. That a potential was commonly applied to the capacitor 1, capacitor 2 and capacitor 3. Right, since these three are in parallel, directly the equivalent capacitance can be calculated using this simple formula: C is equals to C1 plus C2 plus C3. So what we have to do is we have to obtain the relevant equation for this C1 and relevant equation for C2 and relevant equation for C3. Since it is a parallel plate capacitor, just observe what is the equation which is meant for that. The parallel plate capacitor has the equation of C1 is equals to epsilon S by D. That this is a basic equation. Now I want to modify this equation. What is the surface area we are considering for this capacitor 1? The total surface area is S, and that surface area is equally maintained for these three capacitors. So this capacitor will get the surface area of S by 3. The second capacitor will get the surface area of S by 3. Third capacitor will also get the surface area of S by 3. But clearly identify the distance between the plates is in all cases is same. That is nothing but D. So instead of this S, what I have to write down is S by 3. So for understanding, the surface area of the first one is S1. Now I will replace this one with S by 3 divided by D. And epsilon can be written in terms of its relative dielectric constant as epsilon R into epsilon naught. So this can be written as epsilon naught epsilon R1, that is S by 3 D. That this is the capacitance of first one. So simply what I am doing is I am taking the basic equation, just I will modify this surface area what we have which is meant for our first capacitor. So only it is just S by 3, I wrote S by 3 here, distance D is same, and epsilon also was modified as epsilon naught into epsilon R1. In the similar fashion, if you try to obtain the capacitor 2, capacitance for the capacitor 2, what we get is epsilon naught epsilon R2 divided by same cross sectional area we have here, that is S by 3 divided by D. In the same way for capacitance 3, capacitance 3 is epsilon naught epsilon R3 S by 3 D. Just this is the capacitor 1, 2, 3. The equivalent is addition of these three. Therefore, C equivalent is equals to, that what I do is I will take this epsilon naught S by D common. So epsilon naught S by D is common in all the equations, that is epsilon naught S by D, what I am taking common. The remaining parameters are epsilon R1 plus epsilon R2 plus epsilon R3 divided by 3. So what is epsilon S by D? Once again, that is the capacitance without these dielectric slabs. So simply this can be replaced with C. Therefore, C equivalent is equals to this entire term epsilon R1 plus epsilon R2 plus epsilon R3 divided by 3 multiplied with this term can be replaced with the capacitance of our original structure without those dielectrics. So this is our answer. So just what we need to do is we need to observe how the plates were arranged, how the potential is applied. So whenever the potential is common for all the capacitors, then simply remember that all they are connected in parallel. Whenever the charge is equal, then simply remember that all they are connected in series. So if the charge is common, all they are connected in series. If the potential is common or the same, then all they are connected in parallel. That this is a simple technique what we are supposed to remember for this type of physical arrangement. This is the solution for this problem. Problem 4. The capacitance of an insulated conducting sphere of radius r in vacuum is. Just observe what is the parameter which is asked to us, that is the capacitance of an insulated sphere. So only single sphere is given to us. Till now we discussed about the capacitors of two conductors. Just we require two conductors, and between these two conductors a dielectric must be there. But here what he is asking is to obtain the capacitance because of a single conductor, and that is an insulated sphere, a spherical shaped conductor. Now how to obtain? Just observe. Let us take this is the insulated sphere what we have with radius r, and it was kept in vacuum, right? Since it is kept in vacuum, epsilon is equals to epsilon naught, that what we are supposed to consider, right? And it has some radius r. And whenever another sphere which is with another radius and the space between these two spheres is filled with dielectric, we have the formula. So what is the formula for that? The capacitance C is equals to 4 pi epsilon 1 by A minus 1 by B. This 1 by A is the inner radius, and here instead of this r we can take A, right? So B is the outer radius. See, but here clearly in this problem there is no outer radius. So what we are supposed to do is we are supposed to consider the outer radius is at infinity. It has an infinite distance. That there is one more sphere. That sphere has a radius of infinite, and the space between that infinite sphere and the finite sphere what we have is filled with vacuum. Clear? So here that what I am assuming is I have a sphere like this, that is at an infinite location I have a sphere with radius r is equals to infinity, and the space between these two is filled with r epsilon naught. That's the permittivity epsilon naught. It's nothing but vacuum, right? Now simply correlate this data given which is given in our problem. So instead of this a we can replace our r, and instead of this b also we can write infinity, that the outer radius sphere radius is infinity. Therefore c can be simply 4 pi epsilon, so 1 by a now comes to the numerator, that is r. This is a simple equation, Farad. This is our answer. The same question may be asked in another way. Calculate the capacitance of earth. So how to calculate the capacitance of earth? So let us take this capacitance as this earth as a conductor, and it has some radius, and it is clearly spherical in shape, right? And another sphere what we are supposed to assume is at infinite distance from the earth's surface. So instead of this r we are supposed to substitute the earth radius, and instead of this epsilon we are supposed to substitute epsilon naught. All these are constants. So if you substitute them, definitely we will get the capacitance of earth in that particular case. So this is a very simple solution, just we need to remember this equation. Problem 5. There are two conducting plates of sizes 1 meter by 1 meter and 2 meter by 2 meter. The ratio of capacitance of second one with respect to that of first one is. Just observe here what is the data given to us. It's a very simple one. Two plates were given to us. One is of size 1 meter by 1 meter. Another one is of size 2 meter by 2 meter. We require the ratio of capacitance for these two plates, right? So how these two plates capacitances were related? Since these two are plates, clearly we can assume or imagine them as a parallel plate capacitor. So this is a parallel plate capacitor with these dimensions. This is another parallel plate capacitor with these dimensions. And since there is no data given to us, we need to assume that the space between the two plates is same in both cases, and these two are filled with similar type of dielectric material. These two are the assumptions that what we are considering. That is, the epsilon is same for both materials, and the distance between the plates is also same, right? Now can calculate the capacitance because of the first one. C1 is equals to, I am writing epsilon S1. What is S1 here? Simply 1 meter square divided by distance, we don't know, write it as D. That is the capacitance of our first one. And the capacitance of second one, same material we are using as dielectric material, so epsilon, and 2 meter into 2 meter, what it is? 4 meter square divided by same distance. Just take the ratio of these two, C2 by C1 we require. So the second one to the first one, which is equals to, so if you compare them, then obviously the answer is 4 meter square by 1 meter square, which is equals to 4. So the ratio of the capacitance of second one to the first one is 4. This is our answer. So a very simple problem, just with the observation that what are the dimensions of our plates, we can directly say, so 4 by 1, so 4 meter. This is our solution.